going live on YouTube. Yeah, go ahead, Bernd.
Okay. So my name is Bernd Mohr, for people who don't know me. And now I got this interesting challenge. You saw like Damien trying to squeeze 5 years in 1 hour. And I have 43 years I need to squeeze in half an hour. Let's see how we can do. How long can you stay tonight? Okay, let's see. Yeah, as I said, I'm an old guy. Shortly before retirement, I'm working in HPC for a really long time. And this is just kind of like some things which happen on the way. And I basically concentrate on two things. One is my research topic is performance tools. So some tools I worked on, but just very shortly, that you probably just see the name, not much. I don't have the time to go into detail. And of course, we had to test these tools on different machines. And so what kind of machines did I ran into in these 43 years? Okay, so the early years, which was basically, I was in University of Erlangen in Bavaria, Friedrich Alexander University. And I started my computer science study in October 81. So this is for 43 years. And I stayed there until I did my PhD. So that was the first computer I used to. It's a picture from the internet. I never been in a machine room. I'm not even sure it's the machine in Erlangen, but is this how this Telefunken TR4040 looks like? And basically, we used it in like you go computer science. So in the first semester, you learn how to program, and this is the machine we were using. At that time, I was a student, I had no idea about it, but meanwhile, I learned this computer was actually the fastest computer developed in Europe at this time, in the 70s. And it was a dual processor. So I started my life not on sequential programming, but even my very first computer was already parallel. And I found out that we had a special version of this machine. It was the only free processor TR440 in the world I was working on. And it has this amazing huge 1.5 megabyte main memory. And this for the whole university. Yeah, it was just to get you, as it's like everyone knows, like we got quite far in these 40 years. The program was done via punch cards, and I brought one with me. So these are not just some punch cards. These are the solutions to the 13 exercises I had to do in the first year to learn programming. You can look at them, but don't basically, I have no way to sort them, so please. And yeah, you gave basically, you had these kind of typing machines, you got the cards, you gave it in some, there was a window, you gave it to the operators, you had to wait half an hour, and then they brought out printouts of your program run, and this is it's the only thing I found. I thought I had more, but it's like this 130-page letter, so older people in the room probably remember these. And the young people now said, like, why I'm showing this? Have you ever wondered why typical terminal size is 80 characters wide? Because punch cards have 80 characters, and the other 130 comes from the line printer thing. Yeah. A program was done on Fortran 4. It's before Fortran 77, but we used actually Algol 60, and we had a few other things. If you want to learn about this machine, I put some links in there. The interesting article is the Wikipedia on the bottom, but it's unfortunately only in English. It has lots of information about what languages were used and so on. So, but basically the key point was here, I started already working as a free processor system as my first system. Later, when I went into like bachelor, master, and my PhD, I was working as part of a SFB 182, which means it's German for Sonderforschungsbereich, which means like special research project or something. So basically, it's just a bunch of money. The German, is it even the DFG, the German Research Foundation, is giving to a university, and it's typically like for 3 years, and they can extend it multiple times. And so this is, I just want to say, it was 1987. Erlangen was working on a multiprocessor network configuration special research operation. So before like commercial, like Intel or other people even thought about building parallel systems, like the University of Erlangen, which I ended up there just by accident. I was born about 100 kilometers away. It was the closest university who allowed you computer science, so this is how I got there. But I just found the right place. Or you can say it differently. I didn't choose HPC, HPC chose me. Yeah, so like, yeah. And I was part of, because I'm doing tools already, like this is where the tools come from, I was part of a work package, measurement, modeling, and evaluation of multiprocessors and computer networks. The funny thing is, this is not even the earliest day of parallel computing there. So they developing at the university systems, and the first one was ECBA, and this was done in the early 70s. They built the first, I think it was a 5-processor system. And then at my time in the like 70s, 80s, they had a system called DIRMU, Distributed Reconfigured Multiprocessor Kit. And then later when I left, they worked on a 3rd generation, but they never, this really didn't work out. Because at that time, Intel came and other people started. And then for university, it was not enough to get these systems out of family. Another thing, young people, perhaps like, I don't understand, we didn't have laptops. We didn't had, so like when you gave a presentation, you had these slides, you put on an overhead projector. We didn't have something like printer, like a really good, like a slide printer, so you had to like painted your stuff. So this is original slide I scanned in from that time to people when I give a talk somewhere, like where I was living. Okay. And then basically this is the one, the thing I worked on as my PhD thesis. It was a very configurable set of tools to do measurements on all kind of stuff, and I called it Simple. I thought it's a great name. Like it was source-related and integrated multiprocessor and computer performance evaluation, modeling and evaluation environment. And the idea is basically you get all these bits and bytes out of a computer, and you have multiple stages, and at the end you get all the insight. And the problem was the name was not really fitting. So I had all these components. Each of these components could be programmed by configuration languages. I'm a compiler person by training, so everything was configurable. And I guess the only person being able to use the system was me. But we actually, we used it in multiple collaborations, and we even sold it to IBM and other people. And what happened basically is they said they had a specific configuration. I made all the configurations for them, gave them a configured system, and maybe just adapted a little bit, and this kind of worked. And you see some systems we worked on. It was basically simple workstation at that time, and the DIRMU research project. And then Suprinum, I want to talk about, and Transputer. I don't know, some people remember Transputer, so yeah, like we had fun with all of these. So for Suprinum, I thought it's worth mentioning. This was a government project in, yeah, it says here, like late 80s. The German thought we need our own supercomputer. So they put together like companies and universities, and the project was called Suprinum, like Superrechner für numerische Anwendung, or Supercomputer for numerical applications. So we've developed actually a 256-node system in '85. And for a short period of time, this was the fastest MIMD computer in the world. I mean, they couldn't compete with the vector computers, but for a cluster, it was tough. And I could have a node board from that system. Board, fully stacked. And the interesting portion of that was it had a Motorola CPU, and then 3 vector floating point units. It was really for numerical applications, was really, I think, interesting idea at that point. But everything had to be done, yeah? Like we had developed a compiler, the operating system, the message passing, everything. And so if the machine was finally up and running, there were like 2 or 3 more generations of this Motorola CPU, but they built the board that it was not plug and play. So it was a powerful computer, but had like a 3-4-year-old CPU, so they never were able to sell anything. So the project was a total failure, and the government killed it. But what people underestimated is, have you ever wondered why we have so many HPC sites in Germany? Because all the people working on one project got hooked on power computing, and when they went to their university or everyone started doing that. So meanwhile, in Germany, we have like 3 national highest performance computing centers, Jülich, Stuttgart, and Munich. Then we have another 9 national high performance computing centers. Then we have a German climate service, like there's another 10, 15. And this comes all basically of the people which were in Suprinum. There was Parmax coming out of a project. It was a predecessor to MPI. The Fortran system developed was very influential in creating high-performance Fortran later. So a lot of good things came out of that project. It was an interesting machine. Okay, then I thought I need to do something different, and I wanted to go to the US. And I ended up, it's a long story, I'm happy to tell it at dinner time, at the University of Oregon in Eugene for 3 years. The context was I was working in a ARPA project, Parallel C++. Yeah, so it was the mid-90s, and we wanted to develop a data parallel version of C++. But as I said, it was 92, it was a much simpler C++. It didn't have templates yet, it was just basic class, object, very simple C++ classes and objects, and so on. There was two pieces. The group of Dennis Gannon and a postdoc named Pete Beckman, some people might know him. Like they developed the actual compiler, and I was together with Alan Maloney in Oregon, and we developed languages and libraries and performance tools for this PC++, and the name I gave to that was Tau. So some people might have heard of a Tau tool. I come to that in a second. So just this is the idea of this data parallel C++. So you have a class, and when you have a method, it gets called on the object. And then we had special, what we call collections. Yeah, it was basically parallel data structures. We had, I think, vectors, list, and I forgot the third one. And then when you called a method on this object, it was called in parallel on all of these. Yeah, and this is the list of machines. So in the 90s was an exciting time. Like people, it was like everyone tried to build their own parallel machine. So Kendall Square was like a cache-based system, sequence symmetries, CGI, convex, BBN butterfly, thinking machine, Intel Paragon, IBM SB102, Cray T3D&E, Myco, and then workstation clusters. And we spent a lot of time making our language working on all these systems. So it was very portable. It was even performance portable. It ran badly on all of these systems. Yeah, okay, yeah. And so some people might recognize that logo when you're working in tools. So I actually, the first one on the left, this is what I came up in 94. Actually, it was called Tools R Us, and I thought it's funny. But when we talked to funding people, they said, yeah, there's Toys R Us, and people could think this project is a toy. So they asked me to come up with a different one, but I liked the logo, so I changed it to Tuning and Analysis Utilities, which is it's known now. But I have to say, at that time, it was only really working for PC++. In the end, before I left, we made it work with standard Fortran C++, but when other people took over, like people like Samir Shende, who some people might know, and then he made it to the Tau, which is now, but I'm inventor of the logo, the name, and a few things. Yeah, so this was original Tau system. again, I like the Unix way. You have all these little modules and you can plug them together to get more complex things. And I did this, was implemented Tickle Decay. Yeah, Tickle. And the joke here was basically all the tools had to be an adjective, ideally a positive, and with a Y at the end. So if someone said what it's tau, I could say, oh, it's cozy, fancy, cagey, classy, racy, speedy, and so on. Okay. Yeah, as I said, I don't have too much time, so going on. And then it's another long story, I'm happy to tell at the dinner, is I ended up 1996 in Jülich. And as I'm still here, so this is basically my third phase. I came here kind of by accident, but never left, because it's amazing site. You saw some of it here, and amazing people, amazing support, amazing resources. So this is the place to be if you want to be in HPC in Europe. Sorry to say that. There's nice places in the north and in the south, but okay. This is the context for my performance tools. So we wanted to get basically beyond that, measure something, get some numbers, give people a graph or like pie chart. So we want to get further. We call it automatic trace analysis. We wanted to have tools which basically tell you what's wrong with your program. And so we got EU money in the beginning to network. It was called Apart. And then later this developed in something called VI HPS. I think Brian mentioned it. It's still up and now. So I'm one of the funding partners. We do a lot, like basically all major tool developers, but the RISE two people who do the HPC toolkit are members of VI HPS now and do lots of training and so on. The original tool we developed was called CodeCheck. Yeah, like I guess only older people know what CodeCheck is. So it was a police detective I think in San Francisco, and he had also no hair like me, and had a lolly always sliding around, and then he solved cases, like CSI Now or something like that. And the idea was basically this CodeCheck basically gets to your program and finds the bug. Little side story, after a while, I got a nasty letter by lawyers from relatives of Telly Savalas, said I'm not allowed to use his logo. And so we came up with a different new logo next to it. So that was, but this was basically just a Python program at 2006, was kind of like a prototype, working on a laptop. And we looked at systems of a few hundred processors. In beginning worked quite well, but when the system got larger, we added more and more features. And so the analysis took something like an hour or two on a laptop, and then you couldn't use it in a training anymore. Yeah, like they said, let's do exercise, and now okay, go 2 hours coffee. So then, basically in 2006, we parallelized the whole thing. It's now Skalaska. Markus told you about that, also about Scopy and the ecosystem, and it's basically the same thing as CodeCheck, just parallel. And it is, Markus said, we made it so scalable that we could work up to 1.8 million threads. This is the original list, which we supported with the first version of Skalaska. You see a lot of all the blue jeans, K-Machine, Fujitsu, T-Hanye is like the Chinese machines, Intel mics, and all kind of Linux clusters. You see it 32, 64, AMD, Power PC, ARM64, AIX. All of course, basically the upper part is more or less dead besides Cray and Fukaku. And so our main current target is ARM clusters. This was a machine we had here in Jülich when I came. So this is around late 90s. So it was kind of a transition from the vector age into the parallel age. So we had various vector computers, and the most powerful was this T90. I think it had 8 processors, 8 or 10. Liquid cool, very cool. And then we had a T3E, it was kind of one of the nicest machines I've ever worked on. Only the Blue Gene was better. And it was basically a successor of a T3D, but it was basically a very interesting machine. So you had DEC alpha processors, which were arranged in a torus, and you had special hardware on it. So you could do like the first remote, I'm not sure, I'm not a big hardware guy. Some people could correct me, and unfortunately Jeff Hammond is not here anymore. But I thought it was one of the first machines who had this remote get and put in hardware. So you wrote on a register and it ended up in the hardware on another processor. And so the computer was programmed with a libSMA, which was basically the first version of SHMEM, which we know now, and we used that. And we got one machine, and we got even a 512 node system. At that time was quite big. And we were actually only supposed to have one system. But that system, the original version, had a really bad bug. So it had also hardware. It was called streaming buffers. The idea was there's hardware watching your memory access, and if it detects a stride, it automatically fetches it for you in hardware for that. But there was some, I don't know exactly, there was some bug in it. So some programs, when they used the stream buffers, they crashed the system because it was a single system image. So basically you logged in, and when you hit PS, you saw all the jobs on all these, all running on that. So it was, but the thing is, if when one of us basically did like crashing some nodes, it took down the whole system. And so after a while, our sysadmins got a little bit nervous because, like, yeah, someone runs a job, system goes down, like reboot like 1 or 2 hours, next person starts a job, boring, goes down. And it was for a while. And so we had to switch off the stream buffer feature, but it was luckily possible. But then basically the performance dropped by like quite a bit. And we had like the usual stuff, procurement says we have to get a system of so and so much performance. So as a compensation, we got another 256 processor T3E, and later we got some extra funds to even upgrade it. So we had 2 512 systems at that time. And actually, I brought a node board, like liquid cooled. So there's like 4 cores here, 4 cores on the other side. In between is the cooling plate. So that was a 8-core system in 1996. You're welcome to lift it. It's quite heavy, and like I guess most of us have an 8-core in their smartphones. It's quite a development, I think. Okay. We also had a Intel Paragon, which was a really nice machine built by Intel. It had this really interesting LED display on the beginning showing the status of a CPU and the node links. And so you actually experienced programmers could, by looking at the panel, they could guess which application is currently running because of a pattern of the communication and so on. Intel just had the idea that they have to develop a totally new operating system for this machine based on macOS. They never really got it working. So when they sold quite a few machines, but they were really unstable. And we were so unstable, and it's basically in the middle. This is a cut and paste from a slide of our directors at that time. He was so ashamed of the machine, he didn't put the Paragon into this picture, and so on. Yeah, okay. Yeah. This is the machines after that. I think these are newer, so there's not so many funny stories to talk about. So we got a Power 4 cluster and a Power 6 cluster. It was called JUMP. Then we got, this was like a basic cluster. And then we started with strategy that, oh, we want to have a system for normal users, quote, quote. And then for like sophisticated users, highly scalable. So we got one of the first Blue Gene Ls. and then a normal, probably some Intel cluster. Then we got a Blue Gene P and a Blue Gene Q. Actually, there's one missing. So we got all the free Blue Gene machines. Then we got the Blue Genes, of course, unfortunately, didn't no longer get continued. So we had to switch to like more standard clusters. Then the Eureka came, and then we created this concept of cluster booster, which later developed into this modular system architecture, like you heard about that. And you see the current systems, Joules Booster, Eureka DC, and Joules Cluster. And then, of course, like the exascale computer. Okay, so it was like a very, I kind of stayed in time, rush through the 43 years. I worked on so many machines, I probably forgot a few of them. I have much more to say actually on the tools, but there was like last year, someone invited me and I gave a talk, 37 years of performance tools development, and it's actually on YouTube. So if you're really interested in that, like learn more about Tau and Simple and all the other stuff, feel free to look at that. And with that, I'm happy to take a few questions, but I think we should really move them to dinner unless there's some really thing, because we really have to leave by 6:30 the place here. So thanks for listening to the ramblings of an old guy, and but I'm happy that you people who know me. If you don't stop me, I talk forever.
Thank you, Bernd. Like you suggested, if you want to talk prehistoric computing, go sit with Bernd at dinner, and he'll, yeah.
The other thing you need, and let people know, like Hitchhiker Guide to the Galaxy and don't panic, but in some real cases you need the panic button, and so like this.
Okay, for the people who are joining the tour, I think it's easiest if everybody packs their stuff now.
Now we come back here.
You come back, okay. So you leave your stuff here. We'll be back here, well, no later than 6:30, because we have to be off campus by 7.
You know, like you want to be for dinner at 7.
Yeah, for dinner actually at 7. So yeah. Well.
So what we do is basically we make 3 groups. So what we basically we make 3 groups. You can watch here and get explanations what you see in the room, and